Okay, our next portion of the quantities unit, we're going to look at the topic of proportions. And the first sort of subcategory of that we're going to examine is percent composition, which is basically trying to describe what elements compounds are comprised of. So I'm going to start with this question. And if you've got the handout, you can follow along. My question, does lunar water, that would be moon water, have the same chemical formula as water on Earth? First of all, you may ask, is there actually water on the moon? There is. You can find it in the form of ice at the lunar poles. And the answer to this question, does it have the same chemical formula? Yes, it does. It's water. So water, we know as H2O. Think back to our nomenclature quizzes. Water, write down the formula. If I ask for sodium chloride, you're going to tell me it's sodium and chloride. One sodium ion to one chloride ion. If I asked for, I don't know, sucrose, you'll give me the formula C12H22O11. So when we talk about percent composition, what we're examining is what proportion or what ratio elements combine in when they form compounds. I'll give you another example with a bad meme to go along with it. I'm sure you've seen something like this before. Maybe not Chemistry Cat, but probably something else. Here's a bad joke. Two men walk into a bar. The first orders some H2O. The second one says, sounds good. I'll have some H2O too. Rah, 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 rah. The second man died. Why? Pause this for a moment. Think. H2O. H. Two of them. Oxygen. H2O2. I've got water here and hydrogen peroxide. Two compounds that are made up of the same elements, but they have vastly different properties. So water, would you drink that? Sure. Hydrogen peroxide? No, absolutely not. So what we're going to examine with this is the fact that even though we may have some substances made up of the same types of elements, the ratio in which they combine help give compounds different physical and different chemical properties. So I'm going to start off with the law of definite proportions. Lots of laws in science, so maybe you've heard this one before, maybe you haven't. The law of definite proportions states that a chemical compound always contains the same proportion or the same ratio of elements by mass. So I'll give you a couple of examples here, and you can add this into your note. Water, for example. Water, H2O, is always the proportion of two hydrogens to one oxygen, or the ratio of two hydrogens to one oxygen. So that's an O. That's not the number 10. So I can express that. You can see here that I have a ratio, two hydrogens, one oxygen. How about carbon monoxide, that deadly poisonous gas that your red blood cells love so much more than they love oxygen? One carbon, one oxygen, and they always combine in that proportion or that ratio of one carbon to one oxygen. Now let's compare that. Here's my water example to hydrogen peroxide, also made of hydrogen and oxygen, but in this case, I have two hydrogen to two oxygen. So ratio, two hydrogen, two oxygen. Yes, you could simplify that 1 to 1, but as we talked about in our nomenclature unit, we're not going to reduce those down because if we did, I'd no longer have a peroxide ion. And how about we look at this? Carbon monoxide, very, very bad for us. Carbon dioxide, I mean, it's not great. It has its own flaws, but that's one carbon to two oxygen. Okay? So even though compounds can be made of the same elements, the proportion in which they combine give them vastly, well, not sometimes vastly, but oftentimes vastly different properties. Uno momento. So I'm going to go to this as it's just a little simulation that shows the law of definite proportions. So I can carry out a reaction here with hydrogen and oxygen. So what I'm going to do is just pump in some hydrogen molecules. Okay, here's gaseous hydrogen, H2, one of our Haber-Finkels. And let's pop in some oxygen. Now, when these react in a synthesis reaction, in this case, we're going to synthesize water. How this is demonstrating the law of definite proportions is that when they combine, synthesize, there we go, To create water, it always does so in the proportion of 2 hydrogens to 1 oxygen. If we had a different proportion, let's say 3 hydrogens and 2 oxygens, it wouldn't be stable, but for argument's sake, you would no longer have water. That is a different compound. Okay, back to this. So, a couple ways that we can express these proportions is what we're going to talk about. And the first one we'll look at is something called the mass percent. Now, when you think of a percent, let's just do a little minds on here. Let's say you had a quiz. You got 18 out of 20. Take a moment. That's an A plus. Could you calculate what that is as a percentage? This happens to you often. You get your test back, your teacher, usually it's me. I won't do it. Hasn't converted your mark into a percentage. So you get your calculator and then just think to yourself, what do you do to make that value, that 18 out of 20 as a percent? So you're probably going to say, I'm going to divide the top number by the bottom number, what I had correct out of the total marks available, and then you multiply it by 100%. And that's basically the same thing that we're going to do to calculate the mass percent of an element in a compound. So by definition, mass percentage is the mass of an element in a compound expressed as a percentage of the total mass of the entire compound. So in order to find this, we're going to analyze, oftentimes we'll analyze these substances to find out the mass of individual elements, and then we're going to divide that by the total mass of the compound times 100%. And this is just one way we can report kind of how much of a compound is made up of element A and how much is made up of element B. So here's the formula we're going to work with. And it's very straightforward. So here's mass percentage. And what we're doing is we're taking mass, little m, subscript here, I've just put element, but you could replace that with the actual element you were trying to find. So if it was how much hydrogen is there in water, you'd put little m with a subscript h. And on the bottom, we're going to divide that by the total mass of the compound. So right now I've just put a little subscript here that says compound, but when we go through our next examples, we can be more specific. We know exactly what they are. And then we'll multiply that by 100%. Okay, so let's give you a quick example of what this would look like. So let's say we have a substance, a compound. We have analyzed it and determined that the total compound, the sample of this compound that I've taken, it's unknown, is 13.8 grams. And later we can determine that 8.80 grams of that total is iron. Determine the mass percent of iron in the sample. Now I've shown this in full grasp format, but it's pretty straightforward. Here's the mass of my compound. I've just left it as compound because I don't quite know what else it's made of. I've written the mass of the particular element that I'm trying to find, so what its composition of iron is, and then I want to find percent iron. So to find percent iron, I've taken mass. Oh, sorry, that kind of struck out. That should have been like an underline. But there's my mass subscript of iron over the mass of the compound. I'm going to divide those two values and times it by 100. So in total, 8.8 grams out of 13.8, that's 63.8% of this particular compound is made of iron. So I'd say the mass percent of iron is 63.8%. I'm still looking at significant digits. I've got a value here, 1, 2, 3, and here, 1, 2, 3. So the fewest number in both cases is 3. Rules of division, round it to the fewest number of sig digs, which is 3. And that's what I've reported in my final answer. Okay, I think this is pretty straightforward. Okay, now the next sort of permutation of this, or little add-on I might say, is percent composition. So what we're looking at here is if I were to examine a compound, I'm going to report the mass percent not just of one element, but all of the elements in the compound. So here's an example for this one. You have a compound with a mass of 48.72 grams. Upon analysis, it's found to contain 32.69 grams of zinc and 16.03 grams of sulfur. And if I look at those two values, well, luckily, if I add them together, those two add up to the 48.72. So these are the only two elements that we have in this compound. What's the percent composition of this compound? So you're going to notice with this question, I didn't say what's the percent of zinc or what's the percent of sulfur. But when we say what's the percent composition, what I'm effectively asking for is what is the percent of each of the elements present. So let's go to our givens list. Mass of the compound, the sample of that particular compound, the mass of each of the elements in that sample. And what we're going to look for is what's the percent of zinc and what's the percent of sulfur. And finding those two things, percent zinc, percent sulfur, is what percent composition is. So if we're asked to find composition, that's what we're looking for. Okay, I'm going to go to the next portion of our solution. So I found percent of zinc. I'm going to take the mass of zinc over the total mass of the compound and then divide the two, and we'll change it into a percentage. So 67.10%. I'm rounding this at this point to 4 significant digits because I'm just going to report this in my final statement. I'm not using this value for another calculation. So in this case, I have 1, 2, 3, 4, 1, 2, 3, 4. So I've rounded it to 1, 2, 3, 4 sig digs. Then I want to find the percent of sulfur. So what I've done here, again, same formula, just sub out or swap out the zinc for sulfur. And then I'm going to divide the mass of sulfur in the sample by the total mass times 100, 32.90. I look at those two values, there's only two elements. They add up, luckily, to 100%. So then I would say the compound is 67.10% zinc and 32.90% sulfur. And really what you've answered there is what is the percent composition. Now, if you had an example where you had, let's say, 3 elements or 4 elements or even more, we're just going to follow or go through all of these same steps. If I had something with a polyatomic ion, like a nitrate, NO3, I'm going to separate out the nitrogen from the oxygen and find the percent of each individually. There are some examples where perhaps, I'm going to go back to this, maybe you're told the mass of one element but not the other. You could still find the percent of the second element if we just subtract that value from the total. Okay, so let's say, for example, I didn't tell you that the mass of sulfur was 16.03. You could subtract this value from the total to determine that. Okay, so the last, application of this would be determining the percent composition when you don't actually have mass data. So we don't have any experimental masses. We haven't taken a sample and said I have this many grams of the sample and this many grams of an element. So if you have no specified mass given for the compound, the easiest amount to work with is just 1 whole mole of the compound. And if you do that, then what you can do is use molar masses and simply read those off of the periodic table. So I'll use an example here of hydrogen peroxide. So we'll go back to that H2O2. Here's the question. What's the percent composition of H2O2? Now, how this differs from the last question, I haven't given you any mass information, no little m's. So how could you determine its percent composition? Well, I'm going to assume that I have 1 mole, easiest amount to work with. So if I had 1 mole, what I could do is go to my periodic table, add up 2 hydrogens and 2 oxygens, and find the molar mass. There's my capital M for hydrogen peroxide. And then I know out of that 1 mole, there are 2 hydrogens. I can find the molar mass of 2 hydrogens, which would be 2.02. It's 1.01 on the table. So for 2 moles, 2.02 grams per mole. And then for oxygen, again, that's an O and not a 0. I'm going to find the molar mass of oxygen in this compound. Oxygen is 16 grams per mole, and I'm going to double that because there's 2 of them in my formula. So now I've got some values to work with I can compare. I can see in total that both of the elements, hydrogen and oxygen, when I find their molar masses, they add up to my total molar mass for hydrogen peroxide. And then what I'm going to do is find what's the percent of hydrogen and what's the percent of oxygen. So our formula we're going to work with looks very similar. The only difference you're going to notice here, I'm using capital M's instead of little m's. I'm using molar masses instead of just mass in grams. So here I've taken my hydrogen, divided it by the total. Notice I'm making sure I've written grams per mole for each, and then I multiply them by 100% to change it to a percentage. Okay. I'm going to do the same thing for my oxygen. 2 oxygen divided by the total times 100%. The other way you could do this, if you're feeling rather confident, is once I know that this is 5.94%, if you didn't want to go through this whole calculation, you could just subtract that from 100 because there's only one other element. So if I subtracted that from 100, that would give me oxygen and you'd get the same value. So overall, the percent composition we can find, in this case, using that exact same formula, but just using molar mass instead of mass in grams. So that's the end of it. That is percent composition. So it's a pretty light topic, a quick topic for today, but I've picked a few examples from the textbook for you to try. When you're doing these, they do throw in a few tricks. So as I said, maybe they don't tell you the mass data for all of the elements in a compound, and maybe you have to subtract them from the total. Or maybe you have 3 elements or 4 elements instead of just 2. So please go through those practice questions. I've tried to purposely pick out ones that are not all the same. And as I said, answers are in the back of the book, but if you have any questions, please pop onto the Meet and you can ask me. That was a much shorter video than last time. Thank you for listening.